Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to sketch shear force and bending moment diagrams. So let's go ahead and get started. In the given information, we're being told to use the graphical method to draw the shear and moment diagrams. Now, we typically abbreviate this as V and M because we use the letter V for shear and M for moment, okay? So here we have what's called a simply supported beam. That's a beam that at one end you have a pin connection and at the opposite end you have a roller connection. And we just have a single point load acting on this beam, and that has a magnitude of 3 kips, and it's 2 feet away from point A, and then the distance from the applied load to point B is 5 feet. So let's go ahead and get started. If you watch the background video, you might recall that the first thing we need to do is solve for external support reactions. So I'm going to make a note here. I'm going to say first, solve for external reactions. Okay, so how do we do that? Well, we're just going to redraw this beam, and we're going to draw it as a free body diagram. Okay, so we have an AY. We can clearly see that AX is 0 here. And then, of course, we have BY here. And we've got the 3 kips, applied load, and we've got 2 feet and 5 feet. So we're just going to solve for these external support reactions. I'm going to start by saying sum of the moments about point B equals 0. Counterclockwise is positive. And so I'm going to say minus AY times 7 feet. And then I'm going to say plus 3 kips times 5 feet equals 0. And so I can do a little bit of rearranging and solve for AY in my calculator. So we are going to have 15 divided by 7. And we move that to the other side of the equation. So we have 2.143 kips, and that's a positive value, so it is reacting upwards. And then we're going to say sum of the forces in the y direction equals 0, and this is where we say AY, which is the 2.143 kips minus 3 kips plus BY equals 0, and we do a little basic arithmetic here, and we should get about 0.857 kips reacting upwards. Okay, so we have the external support reactions now. Pretty straightforward, and that's just very, very basic statics at that point. So now what we do is we draw the shear diagram, okay? So we're going to make a note here. Draw the V diagram. Now what do? Well, we move left to right and we sketch that diagram. So here's what I'm going to do. I'm going to go ahead and draw a set of axes here. Here's my x-axis that has units of feet. Here's my shear axis, which has units of kips. And so what I'm going to do is I'm going to look back at this free body diagram, and you know I know what AY and BY are, and I'm going to start here. I'm going to move left to right and plot what's happening. So the first thing that I encounter is what? Well, if I start on the left side, the first force that's causing a shear, which means a slicing through the cross-section, is AY, okay? Now I solve for that. That was 2.143 kips going up. So what I'm going to do is I'm going to jump up to that value, 2.143, okay? Now, what's happening from point A just up to the 2-foot mark? What's happening? Well, nothing's happening. The shear diagram is going to stay constant because there's nothing being applied on this 2-foot interval. So we're going to just stay constant at that value of 2.143, okay? And then the next thing I encounter is 3 kips, okay? And that's occurring right at that 2 foot mark. So what I'm gonna do next is I'm going to drop down by 3 kips in my shear diagram. So right now, if you notice, I'm at 2.143, and then what I'm gonna do is I'm gonna say 2.143 minus 3 kips. Again, the 3 kips is pointing down. So in my diagram, what's that gonna do? Well, that's gonna drop me down to, you guessed it, 0.857 kips, okay? And of course, that's gonna be a negative value, right? Because you said 2.143 minus 3. Now, what's gonna happen for the next 5 feet? Well, this next 5 feet is gonna be constant. The shear diagram is gonna be constant. There's nothing being applied here that's gonna change that shape. So we're gonna have a horizontal segment here until we get to the very end of the beam where BY is. And what do we encounter? We encounter BY here, which is pointing upwards, and it is equal to 0.857. So that's going to pop us back up to 0, okay? And so what is this value right here? Well, that's 2 feet. And then what is this value here? That is going to be a total, I didn't mean to scroll there, that's going to be a total of 7 feet, right? Because of the 2 plus 5 feet. And so we like to shade this in. So that is our shear force diagram. Now, what do we do to generate the moment diagram? Well, we're going to make a note here. We're going to say, next step, draw the M diagram, okay? So remember, the change in moment is the area under the shear diagram, okay? So if we think of this as the area under the shear diagram, then what we have here is these rectangular areas, okay? And so I'm going to go ahead and draw my set of axes here. And this is moment in kip feet. There's my x-axis in feet, okay? And so the first area that I encounter in my shear diagram is this rectangle. And what is that area equal to? Well, it's 2.143 kips times 2 feet, right? This horizontal distance is 2 feet. So I can make a little note over here. I can say delta M1 is 2.143 kips times 2 feet. So if you punch that in your calculator, what do we get? 2.143 times 2 feet is 4.286. 4.286. And that has units of kip feet, right? Which makes sense. That's units of moment. So that's going to give me my very first plot on my moment diagram right here. So that's the 4.286, okay? Now, here's the question. How are these 2 points connected? Because I've started at the origin here, right? So how are these 2 points connected? Is it going to be kind of a box shape, or is it going to be linear, or is it going to be curved? What's that connection going to be? Well, it's going to be linear, okay? Linear. How do I know that? Well, think about it. The change in moment, which is generating the moment diagram, is the area under the shear diagram. In our previous video, we saw that that was an integral. So think of it this way. When you integrate a constant function, what do you get? You get a linear function, okay? Now, here's the next question. What do we do next? Because we generated this part of the moment diagram. All right, well, now we need the area of this longer rectangle, okay? So I'm going to say delta M2, the change in moment of the second piece, is going to be negative 0.857 kips times 5 feet. What do we think that's going to be? Well, hopefully, it's the same value we just calculated, but a negative version of it, right? So we're going to say negative 0.857 multiplied by 5 feet. And sure enough, I get a negative 4.286 kip feet, okay? And so what does that negative mean? That means that I'm already at positive 4.286 and I subtract 4.286. And what does that put me? Or where does that put me? That puts me back to 0, okay? And that's linear. So, and I can shade it in like this as well. How do I know it's linear? Well, again, the change in moment is the area under the shear diagram. So what happens when you take an integral of a negative constant, right? This shear piece right here is a negative constant. You take the integral of it, you get a linear decreasing moment diagram. All right, so this is our shear diagram and this is our moment diagram. Let's make a couple of last notes on this, okay? I'm going to change colors here, okay? Notes, all right? So when you have a point force on your beam, that is going to give you a constant shear force, which is going to give you a linear moment diagram, okay? Now, let's think about this again. Remember, because you're integrating, right? You're integrating. You're integrating from load to get to shear, and then you're integrating, or you're finding the area beneath the curve to go from shear to moment, all right? Now, what would happen if you had a uniform load, right? What if you have a uniformly distributed load? So let's make a note here, uniform load. You integrate a uniform load, which uniform load is a rectangular area or constant, okay? What are you going to get? You're going to get a linear shear. And then if you integrate something that's linear, what do you get? You would get a quadratic moment, okay? Let's do one more. What if you have a linearly varying load, right? That's like a triangular shaped load. You integrate something linear, what do you get? You get quadratic. So in this case, we'd get quadratic shear. And you integrate that, what are you going to get for moment? A cubic moment function. Now, which one of these notes did we exercise in this particular example? Well, we exercised this situation. So we had a single point force, we had constant shear segments, and we had linear moment segments, okay? So be on the lookout for my next couple of videos, which may exercise these two notes as well, okay? So if you found this video helpful, please hit like and subscribe, and be on the lookout for other videos that will be explaining similar content. Thanks for watching.